My name's Mark Watson. I'm a grad student from University of Colorado Springs. I work under Dr. Ramatsky out of UC Boulder. He kind enough to take me under his wing, and I've been started out working with the Lattice Boltzmann method in the relativistic regime, and that's what I'm here to talk to you today. I'm going to start off thanking organizers for inviting me here. I haven't been able to contribute, but I've certainly gotten quite a bit out of it. So I appreciate you inviting me here and giving me the opportunity to talk to you guys. Also, I'm a little concerned that the material here doesn't have much to do with, doesn't have enough to do with why we've all gathered here. So hopefully this will be. I'll make it brief, and hopefully maybe someone will get something out of it. I'll do my best. Oh no. Hold on. Nope.
Yeah, it's okay.
No, it's not advancing up there. There you go. Oh. Okay. Okay, so what I'd like to talk about today is two-dimensional relativistic turbulent flow using the relativistic Lattice Boltzmann method. It's something that I've been working with, I guess, for the last several months. The Lattice Boltzmann method itself is a popular and effective solver of hydrodynamics. I'm not sure how familiar you guys are with it. The relativistic modification of it, it's this variance of it that enables you to test flows in the relativistic regime. It's very efficient, good solver. But it's classical. It's classical flow, completely classical. I don't know of a quantum-based version of it, but it does solve turbulence. That's basically what this presentation is about. Is the work that I've done is taking the standard classical Lattice Boltzmann method, taken it, did the changes needed to happen. Not me personally completely, but to move it into a relativistic regime, and that's basically what this presentation is. So it'll sound a little bit like a sales pitch for it, but that's where we're going. Anyway, so short outline of what's going to happen, what I'm going to talk about. Motivation, kind of give you a background of the Lattice Boltzmann method. I'm not sure if I need to do that, but I'll go ahead and do that. And the modifications we made to it, and methods of testing it. Basically, we just want to test it to make sure it's the modifications we made work. So that's all we're doing. Okay. Okay, so the motivation is tried to pull together some motivation here to make it more applicable to this conference. I'm not sure how good I did, but there's some applications. Most of these things I know very little or nothing about, but it's kind of something I want to look into. The relativistic jets, clearly, holographic fluids, I think would be an interesting thing to dig into, and then for supernova. One thing I thought that might, before I got here, before I learned what you guys have taught me about turbulence, is it possibly this might have something, this might be able to tie it in. I don't think it really does, but I thought I'd give it a shot. The graphene, there's possibility that there's the electrons flowing through graphene could be relativistic, and there could be turbulence. So I don't know much about that either, but just kind of read a brief article about it. Okay, so what is the Lattice Boltzmann method? Oh, well, of course, it's based off the Boltzmann equation. The probability, starts off with the probability density function. I'm sure that this audience is aware. And here's this here is the Lattice Boltzmann equation with the collision operator there. The idea is that we discretize the momentum space. So it's it's 6+1 dimensional probability distribution function. We took the Lattice Boltzmann and takes the momentum space and discretizes it. The idea being as the lattice goes to 0, we will completely reproduce fluid dynamics. What we want to do is minimize that. We want to get the minimum amount of information from the lattice from the equations to completely reproduce hydrodynamics using Boltzmann method.
You're discretizing space also, right?
Discretizing, yes. Discretizing space is standard. It's a spatial lattice. The interesting stuff is the momentum space discretized, and then of course time.
So is this a good method to work in the kind of gray area between Boltzmann regime and then viscous? It
does handle viscosity inside the. Is that what you were asking? I don't apologize. Yeah. The viscosity is
like upper atmosphere, where systems which are very dilute, at least the transition.
There are some limitations. So I don't want to answer that question, to be honest with you. But there are a few limitations. I believe it's been used. It's been used in a lot of different realms. So I believe it's they have used it in very pressful situations, but I don't.
When you discretize momentum, you discretize the velocity too, because velocity is linked to the momentum, correct? Yes. So this means that if the scalar product is in certain directions discrete, it's not confused.
Yes, and I'm almost using those terms synonymously.
I'm sorry.
I almost accidentally use those terms synonymously a little bit. I think in this presentation, yeah. And there's a lot of literature on it that it was not that long ago. It was brand new to me, and I read a lot of information about it. One of the good things about it, it's simple, clearly local, therefore it's parallelizable. So what happens is we have the lattice nodes, standard X, Y, Z kind of lattice. All the information, there's depending on how you do it, there's X amount of probability distribution functions per node, and all of the ugliness, all the calculations are in each individual node. So so what you do is you make all the calculations, and you could parallelize it up to the number of nodes you have if you have a strong enough computer. So and then once you do all the ugly calculations, you stream it out and go to the neighboring nodes.
I understand that in this formulation, for each momentum, the coupling is only in the collision integral, correct?
Yes.
So basically, you write an equation for each momentum, you solve on a node,
yes,
and then you collect information for the collision integral.
Yes. Yes.
How many momentum do you
have? It depends on what you want to do.
Order of magnitude 10, 100, a million.
Order of magnitude 10. So 20. I used 27 plus 1. 26 plus 1.
It's a small number.
Yes. Yes. The one I'm going to show you here is 19. There's a certain amount of numbers, and I'll show you how you figure that out.
So just I think maybe related question. So it's local in position space, but in momentum space it's highly non-local, right? Because various momenta will be coupled because of the collision term.
Let me see if I can answer that question in one of the next slides, because I'll have a little graph. I don't know if I can. I think I could do it better by pointing and. Let's see. It's got a physical basis. It solves viscous fluid dynamics. It is stable even with shocks because it's probability density. It does get a little unstable. I think that's the larger disadvantage is as you get closer to higher Mach numbers, it starts kind of getting a little unstable.
What's the reason?
2 or 10 or 100.
Unfortunately, I don't have. So, I'm sorry.
But have you tried?
I've run it and I try, I'll bump up the force a little bit, and okay, that's good. Bump up the force a little bit. Oh, that blew up. I'll get out. So
you don't remember.
and it just
what
kind of
value.
well, and it's in lattice units, so it's kind of hard, especially up here, on the fly, kind of figure out what the units are.
So what works better than something where you have an adaptive creator? So if you want to do high Mach numbers,
If you, if you want to do it, you got to make it. You're limited to lower Mach numbers, more or less. I think. Just like, I'm sorry. Okay, well, here's where I was going to try to answer that first question. So basically, you go through all the formulations, you take a Lattice Boltzmann. Now, with the way it works is you discretize the momentum space using the Gauss-Fermat flucture. You figure out what the speeds are based off, and you get the roots of the polynomials, and that determines the number. And I'll kind of explain how that works in the next slide. So this equation right here represents a single Lattice Boltzmann for a particular speed. So this right here is the node, is the probability density function for this node, for one of the speeds, only one of them. So there's 20, in this case, there's 19 of them. And so here's the probability density function for that, for speed 0 or whatever, speed 1. We get the equilibrium equation. We do this as a collision operator. The viscosity is inside the relaxation time there. And then that tells us what the speed is for the neighboring, I'm sorry, the new probability distribution function for the neighboring node. Is that?
So I actually do have a detailed question. So this is using the relaxation time approximation for the collision integral, right? Because
Yes.
you're replacing F.
Yes.
But in principle, the collisional integral will be the full integral where all p's couple with each other.
Yeah, you could. From what I understand, I've never seen the original Boltzmann integral,
Okay.
but I hear it's pretty ugly.
Yeah.
And there's modifications of this with multiple collision, with multiple relaxation times, different kinds of neat things that you can do with it.
You don't have the gradient in the position, do you?
He has.
Which was the previous slide.
That kind of. I knew you were going to ask that, and I prepared myself to show you how you derive it, but it goes away once. I can show it to you on a.
I think it's basically as you're describing it in the lattice. Okay, so the velocity of the cells is such that in one time that you move the mass from one cell in space to the next one.
Yeah, but then you'll couple different positions.
Yeah. So basically, when you advance, it's like you're following through the cells. So you just have to distribute the masses.
Yes.
So this is an exact scheme you want for diffraction. If you want delta V times delta
No, but
V,
then
it's equal to
the
the mesh
access to the
size.
mean field will be okay. But if you have the mean field too.
But this is exact. I think if you just take the gradient, you write it in a discrete form, and then
No, you go into the reference frame where the fluid moves. This is what they're telling you.
no. I'm telling you that delta V is equal to delta X divided by delta T. So if you discretize everything, it's just what is written there. It's just
Can you go back to the step where we show the equation? Yeah. You see, is the second term in the equation E cross Laplace, a true gradient. You see, I don't see the gradient. You see that as, not that one, no, the second one.
that one.
Yeah.
but this is a transport term. So basically, it's a discrete lattice. So if you're moving the mass from
No,
one
it's
point to
speed in momentum, not in space.
yes, but the momentum, okay, is such that in one time step you just jump from one cell to another. So it's just distributing the mass.
That will couple density distribution at this point with density distribution at this point, which in that equation is not present.
No, in the next equation, he has that.
No, but if you
the
compare it
burden.
with respect to X,
If you go to the, here he has it because it's X plus CIT. So he's coupling different.
But what is the mean field there? That's the problem.
The
I
actual,
should see the mean field too, but I don't see that.
That means, sorry.
Well,
The mean field?
I mean, the last of the third term. The third term
Oh.
that you have in the equation
Where's that go?
on the left-hand side.
So is it force free in this final?
Yes, yes, I'm sorry. That is true.
No
Very
force.
good. In this particular one, it's
No force.
it's force free in this
Okay.
collision operator. It's
Okay.
force free. Yes, and I got this from books and things like I'm not thought about putting it in there, but I didn't want to put it in there wrong. So yes, I apologize. It's force free. Okay, so the idea is that all the fluid dynamics are obtained from the moments that you get from the lattice. So what you do is once you get the probability distribution functions inside this node, you just do an integral across discrete integral across the momentum space, and you get all the mass density, momentum, and all that good stuff. Usually, that's what. Important to note, equilibrium equation is this. So I want to talk about quadrature for a second. Just this was brand new to me, so but I put it up here. Basically, the idea is that provided you take a function. A function looks like this with a regular function, and it has a form of a weight on it. You can estimate the integral of this function. This is 1b here, but you can estimate it by picking the right abscissa, and picking the right weights. You can estimate it fairly well. And it turns out that for Gauss-Hermite quadratures, if your weight function looks like that kind of form, you can take the Hermite polynomials, you can get the roots, we'll talk about later. So the roots will identify what your x's are. Choose your weights like this. And you can this integral right here, do it this way, this integral is exact. Up to, if you choose this number, the right number of abscissa, with the n right here being your the top of the power of your polynomial, or your polynomial, excuse me. So it turns out that's a Gauss-Hermite quadrature. So that was brand new to me. So then we move into basic. So the Lattice Boltzmann's been out there. They've been doing that. One I saw was in the, I think it was in the late 80s as well. One of the earliest ones I've seen, but there's a lot of literature, so it could be older than that. What we did is we took that there's several variants for several different reasons. One of them, the one we're talking about here, is a relativistic variant done by Ramadsky, Mendoza, and Fucci, 2011. This is what I've been basing my work off of. Basically, it's the same kind of thing, except we're in an 8 space instead of 6+1. And here's the relativistic version, also force-free, with its own equilibrium equation. It looks very similar. There's some differences clearly, but same kind of thing going
You
on.
have the crystal symbols which appear only in general relativity. Why? Because you apply it to black holes or something like that?
Yeah, just to be general, just to say it's the general version of it, certainly. The problem that came out was this right here is the form of the equilibrium equation in the standard classical Lattice Boltzmann method, and it's different now. It's Güttner, is that how you pronounce it? So that's the it's a different form, and it doesn't look right. It's not quadratic in the same way. So what was done instead of Hermite polynomials, we switched over to Legendre polynomials. Same kind of thing. It has its own weighting function, and it all kind of works out. And so the lattice changed from this to looking more like this. This is a quarter of it, so it's more circular in nature, and that's how it works. And what I did was I added the forcing term. I probably should have put it in some of the original slides, but I added the forcing term. Same Same thing, get the, got the Legendre polynomials, plugged it in there, got the, and used Gauss-Riemann quadrature to figure out what the intervals are to get the coefficients there. And so now, once we got done with that, now we, in theory, have a fully relativistic solver. Okay, so this was also new to me. So I'll throw it up there. Not new to anybody else, but the idea of turbulent flow, the energy cascades of turbulent flow. So up here you have in 3D turbulent flow. Since it's nonlinear, the energy cascades in the direct cascade, so it goes to the smaller scales, larger wave numbers, whatever you want to look at it. That's in 3D, but in 2 dimensions, it actually the energy goes back to the longer scales, the smaller wave numbers. But the rotational, the instrument tends to restores and goes back to the direct cascade in 2 dimensionals only. Things about that. So that was new to me. And the interesting thing, what we're trying to do is I want to see if I can reproduce relativistic turbulent flow power laws. I want to make sure it's working by seeing if I can reproduce the power laws, the Kolmogorov, Kreitman normal power laws. And so just kind of quickly go over those. Basically, if you drive the system at this wave number here, the energy will propagate to the larger wavelengths all the way to the boundary here, and it should match the power law at -5/3. Additionally, for the rotational driving it right here, there will be a direct cascade, and the power law for that energy should match that -3. Stuff here. This one right here, the -3. There's a logarithmic correction that I don't have in my slides. I put it in there, but that's basically what we're looking for. I want to see if I can match those things to make sure it's working right. Okay, yeah. So again, we want to see if it's going to work by matching the power laws. However, just want to let you know we're not doing super relativism. Haven't gotten to test the super relativistic speeds yet. I'm trying to make sure that the solver actually works under normal speeds at this point. So that's where we're at. Okay, so the way I generated the force was I created a in K space, created a random force field, just random directions and magnitudes in K space, and then I applied a filter. So basically, this one right here, low end filter, it's everything in the smaller the smaller wave numbers, the larger scales, and then of course to the high band filter, the same thing, the opposite. If that kind of makes sense. So I generated that in Fourier space, and then I did a standard, normal fast Fourier transform. So now we got the 2 different fields, and this is in XY space.
Just one question: did you use a sharp cutoff, or did you use a sharp cutoff in the momenta to select, or did you?
Discrete or sharp?
Yeah, that's true. Okay, yeah, that's true. Okay.
Well, you can smooth it over a couple of levels.
Discrete. Same ways.
So here's the results. Here's what we got. Just to see if it matches. It's for the high band filter, so everything low up to a certain driving point seems to match fairly well. Not 100% perfect, but you can see here it goes with the line, and then here's where we're doing it driving at 4 and 6 in latitudes. So you can see where it kind of jumps up there, 4 and 6. Seemed to perform pretty well. The entropy, the rotational, didn't do quite as well. Depending on what range you're looking at, there's over here is 0.24 right there. So we kind of got a curve going, so it wasn't quite as right. I did, there is, of course, that logarithm correction. I put that in there yesterday just to see if that did anything, and it didn't make a whole lot of difference, so I didn't change the slide. So that's the results. Okay, so I feel like up to a certain point, at least so far, I feel like it's fairly stable. At least for the inverse cascade, it reproduces parallel frequency, so I feel like it's pretty good. And so I think we're kind of on the right track. So I'm still working on it. Clearly, I'm going to do larger volumes, stronger drives, get closer to relativistic speeds. I want to look at intermittency, just some correlation functions. I just understand there's some parallels there that I could probably compare as well. Three-dimensional, move up to three-dimensional lattices to make sure that works. Then, of course, move up to relativistic speeds. I really appreciate you guys' time. Any questions?
All right, thank you very much. Excellent.
So can you see the velocity field in space? What does it look like?
What does the velocity field look like in
You
space?
see like, in classical turbulence, people see like regions of concentrated vorticity. They call them blobs. Or
Yes.
bodies. Can you see them with this method?
Yes, because I can. This isn't. This is the force, clearly, but I can. I haven't. I don't have a movie or anything cool like that, but I can dump out the velocity field and determine and build the arrows in that way, and then kind of run that on a loop. I don't know.
So is it you get something like
And so the question is,
or you see intermittence, you see localized.
that was one of the. The answer to that question is that I don't know, because I hadn't done that analysis yet. That was one of the things I wanted to look at intermittency, see what the field looks like. I hadn't done that yet. I think that's just because everybody else, some of the movies that I saw there, you could see where the vortices were and how they changed and everything. And I haven't done that analysis quite yet, and I would like to, for sure. You do see kind of, yeah, you can kind of see something really. Also, we're doing a very small resolution at the moment, so it's harder to see them. I just haven't looked for that yet as an answer to that question. So.
But it's parallelized. The code is parallelized, so you
Yes.
can look at.
Yes, yeah. So the way, yeah. So you take the lattice, you run the calculations on every single node, and you can do that in a parallelized fashion, and then you stream, which means you move all the results of all the calculations to the individual nodes, and then you can and then you take a picture of it, dump it out into the file, and then go on to the next one, so you can see how it evolves over time.
How is it broken up and distributed amongst?
The way I did it was we're using a cluster at the CU Boulder.
But I mean, how do you divide up your space? Like what goes on one node?
Every node has 20, in this case 27 distribution functions.
Momentum.
Okay.
Yeah, it's each one of them represents its own momentum, and they all have, and it's just probability distribution function. And so the x is the x and y and z are the location of the node, and the time is the timestamp it is. And
So every node has all x, y, and z, but then only a few of the momentum.
yes, that is correct.
Or is it the opposite?
I thought opposite. Every node has
every node,
one.
well,
X,
every
Y,
node
Z.
is every node is an x, y, and z, and every node has
all P.
27.
Okay, so every node has all the p's with the x, y.
Yes.
Okay, and then you just need to communicate when something moves.
Yes, yeah. After you get all the calculations, the way it works is every node actually has however many times 2, and it has the f new. So you calculate it and dump it in f new, and then at every node, and then on the streaming function you push it off to the other nodes, and there's collision. There's walls and boundary conditions you have to happen with anything. And also in the relativistic regime, there's some weird calculations because the distances are a little farther in some cases than they are in others. So,
What is the performance limiting? Is it the communication?
That's a good question. Performance limiting.
This is relatively small.
Yeah, but I don't know when it scales up.
I don't.
It's memory.
In 2D, if you want to go to 3D.
In 2D, even in 3D, it's relatively small.
It's it takes a lot more memory, but you can put as many processes.
He has a finite number of moments.
Right.
He has 27, correct?
Yes, that's-
27. So he has basically 27 distribution functions in 3D. Those are not
Yeah, that's-
20.
Yeah, but then how many points you want to put in space?
Yeah, per node. Yeah.
So turbulence,
How many do you want?
1,000 cubes.
Well, in his case, I don't think it's 1,000.
No.
Yeah, we're doing it really small at the moment, but
I'm looking.
Yeah,
But the
but
power-
ultimately, if you want to talk turbulence,
No,
you
yeah,
need
yeah.
1,000 cubes.
Right.
Yeah.
This
Well,
point seven.
And then the 27 is not going to be enough at some point.
so what I have been doing 128 squared lattices to get, yeah, there's pretty small stuff, and I run 32 experiments, 32 runs per experiment, and I run 4 experiments, and I'll kick that off at when I get home from work, and then come back home from work the next day, and they'll be done. But I did a 1024 once, and that took well over a week to get done, which I guess is
I have a conceptual question concerning the collision, because without that, right, the problem is the moment uncoupled distribution functions and mixing this because of collision. And you have only 27 points to mix them. How efficient is that method to realize thermalization? Because I can start, for example, everything in one momentum. You see, state, put all particles moving with one momentum. Do I reach thermalization in this way? Is it relatively fast, as expected? Is the angle to obtain the thermal distribution? Because 27 feet is relatively small number. I have no experience in this one. I'm asking.
yeah. I'm afraid I'm not able to answer that question either. Thermalization.
Yeah, the idea seems good to do it because it's very economic.
Mm-hmm.
But now the question is how, from a physical point of view, how efficient this is to describe the real dynamics. So instead of doing the collision integral, because collision
It's a big one.
Yeah, but you have to keep in mind you're not solving Boltzmann equation. It's not a gas. It's just a method to simulate the response.
no, if you put the collision integral, then you'll solve it.
Yeah, but you don't want to
You
solve.
see, so the question is, you see, how well can I simulate that with a discrete
27.
base space, and then using on top of, momentum space, and then on top of that, putting the relaxation.
So
You see, so I have, you see, it's a pretty strong.
So in turbulence, you have basically 2 important time scales.
I'm sorry?
In turbulence, you have 2 important time scales. One is the inertial time, that is the typical time of large phase. And the smallest one that is related to molecular dissipation. Okay? So it's called the Kolmogorov time. Usually it takes a fraction of all the order of the Kolmogorov time. Okay? But it's a fast, very fast time compared to the eddies that you want to look at the system. Okay? So it's fast enough in order to solve the inertial range of turbulence.
But I don't think you answered my question. How efficient is discrete Boltzmann equation?
Very efficient. That's why it's used in engineering.
So what's the criteria? When can I use it for my calculus?
Let's see.
You cannot use it if you want to look at the velocity gradient space. Okay?
You mean from point to point, right?
Yes. But you can use it if you're
So I
looking at
don't
the
have heat
velocity.
transfer. So I don't have heat transfer, right?
Hmm?
I don't have heat transfer.
Not really.
No heat transfer.
So it's a system that is a model that is really used a lot of in engineering because of so basically you can put a very complex
So
geometry.
you basically simulate systems where the temperature is fairly constant, right?
Okay, here is in particular is that there is no notion of temperature, real temperature.
No, you can local.
local fixtures that.
Yeah, we get local
So what you're saying is I cannot define this. I shouldn't have gradients of temperature throughout the system, which are big.
One side. And I don't know this that much because I just hear by osmosis.
Yeah. Definitely pulling out temperatures with the relativistic, where we do the integration, we get the energy stress tensor, and we get he has a way to interpolate what the temperature is.
Yeah, the reason I'm asking is,
But it's local.
think of, you see, I know Paul Romashka is his advisor. He's interested in relativistic collision. And you have two cold nuclei colliding at very high speed. You form a very hot spot here, which eventually propagates through the system. Everything is relativistic. Everything is very complicated. But then you'll have lots of energy transfer, momentum transfer, you see, especially longitudinal direction, transversal directions. So another question is, would this be reasonable to use in that case? Because so you say, for example, you say, I don't know, because he wants to use it for that. But you say that the heat, you see, heat transfer is not well described in this case. Probably that means only
There is
good for that.
for the notion of heat in this model is fiction, it's not real heat. Okay, so it's
No, heat, you see, you have certain local temperature here, another temperature here. So another question is to equilibrate. You see, this system, you transfer the energy from here to here. You know, there's heat.
yes, but it's not. But anyway, you're modeling a fluid that has constant temperature everywhere. Okay.
Well, that's
This would be
but
modeling.
that's
And
not.
the heat you get in this collision of the model modeling of the inertial temperature fixed heat in order to get a local thermal maximum distribution at each node. That is a discrete system. So this lattice moment comes from something that was called lattice gases.
Mm-hmm.
It was developed by Frisch, Pomeau, and
I don't remember who.
another.
Yeah, it came out of that.
And they do that with
Booleans.
integer numbers in a lattice.
Yeah.
Okay. And they show, okay, basically we can do a fluid just without cellular automata. Okay.
No, I understand this in what you can do forward. The question is, I want to translate it to physics. I want to see the limit state.
And
That's the
it's a
problem.
small scales. Small scales. Okay.
You can do, if I'm not wrong, cannot do to, I mean, you do only moderate Reynolds number.
Usually quite large. They are doing a cube, several thousand cube points.
Yeah, we're doing some pretty high rules. Good use it for turbulence.
It's a very powerful tool for applied situations in particular. And
Hopefully, if you know exactly what it's powerful for. You see, this my problem. I don't know exactly what it's powerful for.
I apologize. I'm not enough of an expert on it.
so, for example, if you want to look at finite time singularity equation, you will never
Absolutely,
get
fine.
time singularities, okay, of order of Navier-Stokes. This won't be the proper way, okay. But if you are looking, you want to solve the flow around an object, that's can make it super well. For the relativistic case, I have no knowledge in that, no experience. Not even imagine what the physics there.
Just to understand, so you're saying there's no temperature because it's essentially built into these
So
factors.
it's okay. At least for the classical version.
Yes.
Okay. So the idea is you want to solve Navier-Stokes.
Yes.
How can you do it? Okay. You can just find a difference of the spectrum or Lattice Boltzmann. Okay. And for Lattice Boltzmann, you say, okay, I will generate a fictitious velocity space. Okay. Such that when I average over the velocities, I get a field that I will look in the physical space. That is a solution, at some extent, of Navier-Stokes equation. So this notion of temperature is it's not a physical temperature. Am I right?
Yes, yeah.
Okay. Okay. Any other questions? We can chat more about this afternoon. All right. Thank you.
Thank you.
So reconvene in 20 minutes.
Do we need a break or should we just?
Well, you announced it to them.
I did.
So I think that's probably the right thing.
Okay, so we'll reconvene in 20 minutes for the next stop.
Thank you for your help.
Is that in